Today we're going to talk about eliminations, specifically the co-elimination and the Hofmann elimination. Both of them start with a tertiary amine and eliminate the starting material to an alkene. For the co-elimination, it starts with MCPBA and then uses heat to finish the reaction. For the Hofmann elimination, we use methyl iodide to start the reaction and then heat to finish it. We can also add silver hydroxide to react with the iodide in the solution, but for the sake of the mechanism, we're not going to focus on it or mention it. So for the co-elimination, what happens is we start with MCPBA, or any compound of the form RCOOOH, which is what MCPBA happens to have as a formula. So the lone pair of the nitrogen will tap the oxygen, the alcohol group of MCPBA. This gives nitrogen another bond, meaning it's a quaternary amine, and it has a positive charge. Now what happens is the base comes in and deprotonates the hydrogen on the alcohol. This means the oxygen is negative and the nitrogen is still positive. So, as with eliminations we've looked at, we talk about the alpha and beta carbons. So, as a refresher, this is the alpha carbon, which means this is the beta carbon. Now, like in eliminations we've seen before, we are going to deprotonate the beta proton in order to get our product. So in the co-elimination, the oxygen will attack the hydrogen, the beta proton, I should say. Now, the electrons from the carbon to hydrogen bond are going to swing down to form our double bond. And from here, the carbon to nitrogen bond, those electrons will go and form a lone pair of nitrogen. This sets up a 5-membered cyclic transition state, as seen here. So the hydrogen-oxygen bond is forming. Oxygen is still negative, at least partially. Positive charge is still on the nitrogen, and the double bond is forming. This then leads us to our final product of an alkene. So, if we go over to the Hofmann elimination, we start in a similar way, which is that we start with methyl iodide. The nitrogen attacks the methyl group, leaving the electrons to go on the iodide. This is where the silver would react with the iodide, but again, we're not going to focus on it. Now, we have a quaternary amine because of the added methyl bond, leaving nitrogen to be positively charged. And this is where we're going to have an E2 reaction, as we've seen in the past. So we have our alpha carbon and our beta carbon. So we're going to deprotonate the beta proton. And in this case, unlike the co-elimination, the Hofmann elimination requires the proton to be anti as well. So we can deprotonate with a base anti-beta proton. The electrons from the carbon-hydrogen bond will swing and make the double bond, and the double bond will force the carbon-nitrogen bond, those electrons, to go onto the nitrogen and make a lone pair, leaving us with our final product. So, two important things to note. With the co-elimination, the products that are favored are based on the amount of hydrogens on any beta carbons that are in the starting material. Whereas in the Hofmann elimination, the product that is favored is the most substituted alkene. And another distinction between these two reactions is in practice, the co-elimination works in much lower temperatures than the Hofmann elimination. But these are our two mechanisms, for our Cope elimination and a Hofmann elimination. Let's practice. Given this reaction, is it a Cope elimination or a Hofmann elimination? Well, if we look at the starting material, we can see that there are two anti-beta protons, which we can check by drawing the proper chair conformer and seeing that they both are indeed anti. However, when we look at the product, we can see that the alkene is in the least substituted position for the given two beta carbons. Now, if we also look at the reagents, we can see that MEI is used rather than maybe MCPVA. This indicates that we have a Hofmann elimination rather than a Cope elimination. That is all for today. See you next time.